Okay, so for this part of the investigation, you have plot A, which is the amount of vegetation removed at first. So this is the starting biomass, and plot C is the ending biomass. And plot B, this is the one that has been covered. So it has not been photosynthesizing at all. So the difference between the start and the end is 39 minus 35.2. That's how much it grew in the week that they left it. So how much it grew, that's your net primary productivity. Amount a plant grows in a given time, so in this case a week, for a given area. And it's really important that we have these three values: the amount that it grew, so in grams, the time, in this case in a week, and a given area. And if we don't pay attention to all three, we can go wrong. So if we subtract this, we get 3.8 grams. So this is the amount it grew in a week. But when we look at the given area, the amount that these students were doing this for was for 0.25 meters squared. So a quarter of a meter. So in here it grew 3.8 grams. Here it wants to know my units in meters squared. So for the given area now, I'm going to know this for a meter squared, which is like this. So this is 4 times the 3.8. So I need to do 3.8 times 4, which gives 13.2. Sorry, 32, and then 3 4s, 12, 15.2. So 15.2 grams, because we saw the amount it grew, per meter squared. And because it's per, so we've missed out that per, that's why that negative is in there. So assuming that MPP and respiration stay constant throughout the year, now we're changing the time. We looked at it for 1 year. Now we want to look at it for 52 weeks instead of before 1 week. So our annual NPP, in 1 week, we said that we had 15.2 grams. So 15.2 grams per meter squared in 1 week. And now we're going to do it by 52 weeks, which is how many weeks in a year. So 15.2 times 52. So look up your calculator. 15.2 times 52, 790. And now grams per meter squared per year. And again, notice I missed out the per, so I make that -1 up there. For respiration, let's go back to this respiration question. We need to show that the respiration in 1 week is 8.4. This was the one that was covered. So covered 33.1. And we know that if it had not, the amount that it lost in that time is the amount due to respiration. So 33.1 and 35.2 is what it started out at. So it's like the graph went on a diet. Okay, so subtract 1, 2, we get 2.1 grams that it lost. It was burning up its fuel, it burned up 2.1. But remember, again, it's only for 25 centimeters squared. This is a quarter of this meter squared. So 2.1, and we need to see how much it would be for a whole meter, because that's what the question asked us there. So 2.1 times 4 will give us 8.4 grams of carbon per meter, because we did it for a whole meter. go forward again to our next question. We want to know for a whole year, and so we'll do the same thing, 8.4 grams per meter squared in a week times 52. Which will give us 436.8 grams per meter squared per year. Now I need to calculate annual gross primary productivity. It's annual, so it's 1 year. So I'm going to use this data in here. This one here is respiration. This one here is net primary productivity. To get the GPP, it equals MPP plus R. So that's 7 GPP equals 790 plus 436.8. One, 226.8. And again, do not forget your units. There are 2 marks down here. You will lose a whole mark for not putting in your grams. It's grams of carbon per meter squared per year. Why would MPP and respiration not be constant throughout the year? Whenever a question asks me about not being constant through the year, the first thing that comes to my mind is the seasons. So when I think about the seasons, the things that I think will change with the season would be rainfall, temperature. Okay, and other things could happen to the amount of daylight could be changed. My fallbacks are always rainfall and temperature, but the amount of daylight could be affected too, and there'd be other variables you could think of. But how would these then affect the productivity? So productivity, so rainfall, so less water. If water decreases, then productivity will be less, because productivity is all about photosynthesizing. With lower temperatures, the reactions happen slower, so processes don't happen as fast. Plants are adapted to specific amounts of daylight, and they need the sunlight for photosynthesis. So these are different things that would vary, abiotic factors that would vary throughout the year with season that would affect productivity. Notice that it asks you for 2 reasons, and you get 2 marks. So you don't need to go into a lot of detail. You suggest a reason, you get a mark. 10% of net primary productivity is available to the next level. Calculate the energy available to consumers from the study site in grams per meter squared per year. Give your answer to 2 significant figures. So if we look at our net primary productivity, we've got to go back up here. It was 790 grams per meter squared per year. So 790. And they're only going to be able to pass along 10% of that. So 7.79.0. It says 2 significant figures. Okay, so I only want to put 79. And I've got to remember my units, grams per meter squared per year. Okay, we don't have to do this question. And that's the end of this one. If you are interested about this, the assumption in part 5, if we assume that 10% of MPP, so 10% of MPP, basically the human population, if we're only passing along 10% of the energy that's being fixed by the sun, and the human population is eating what? Hamburgers, okay? So if you're eating a hamburger, you're eating the consumer of the grass, like the cow. And the cow is only going to give you 10%. So you're actually getting 1% of the energy fixed by the plant. So this incoming energy, a certain percentage of it gets fixed, something like 1% of the incoming energy gets fixed by the plant. And then of that, you're only getting 1% when you eat this beef burger. If we wanted to be more efficient about feeding the growing human population, there's an argument that instead, if we ate plants, we would be getting 10% of the energy fixed by the sun. So it's far more efficient to eat as a vegetarian. Of course, the issue is, and you don't need to answer this into the question, but I mean, how we get enough protein, and you're going to have to eat certain kinds of foods like beans, mushrooms that contain higher amounts of protein to meet your needs, specifically for your cells to function, for your tissues to grow and be healthy. But in terms of the amount of energy you need,